All right, so now we're going to get this thing called variation, direct variation and inverse variation. You can sometimes hear it varies directly, varies indirectly. So direct variation sometimes is said as varies directly. And then inverse variation is varies indirectly. And so the only thing that you really have to remember is there's some constant in here, k. Some constant, we can call it k, we can call it z, we can call it anything you want. But so when it's direct variation, you're saying y varies directly as x, so it means some number times x, okay? So this is varies directly, y equals kx, which is you've seen already, it's like linear equations, parabolas can do that, anything like that. Okay, and then inverse variation is the exact same thing, except for its division, so k divided by x. So direct variation is multiplication, and inverse variation is division. So if you can remember that, you can set these all up, and then the great thing is you can just use your calculator for it, okay? So you have to read the words that are being said in there, and then translate them into these problems. So here's an example. Suppose a ball is dropped from the top of a building and we know the distance it travels varies directly with the square of the time since it was dropped. The square of the time, that means t squared, since it was dropped. At 1 second, it has fallen 4 meters, and at 2 seconds, it's fallen 16 seconds. Find out how far it's fallen in 10 seconds. Okay, so we go 1 second, this is time, is 4 meters. Distance is 4 meters. At 2 seconds, it's 16. Find out how far it's fallen in 10 seconds. Okay, so we've got to set up the equation first. So varies directly with the square of the time. So distance varies directly with the square of the time. So we say distance is going to be our d, varies directly with the square of the time. Distance equals kt squared. Okay, now we're going to use these points to figure out what our k is. Okay, so we plug in 1 for the time and 4 for the distance. 4 equals k times 1 squared. So going through this, we figure out that k equals 4. Okay, we test it with this point right here to make sure that this is true. So distance equals, so in this problem, the distance and the time are changing, but this is, we call this k, we call it a constant. Okay, so the distance equals 4t squared. Once you figure out what k is, through the rest of that problem, it's going to be that. So we test t to make sure that it gives us the distance of 16. So distance equals 4 times 2 squared. Distance equals 4 times 4, which is 16. So it does work out. So now all we got to do is use this formula, distance equals 4t squared, to figure out what time or how far it travels when it goes 10 seconds. Distance equals 4 times 10 squared. We're just replacing the t with 10. So this is distance equals 400. Perfect. All right, the cost of a phone call varies directly with the length of the call, m, in minutes. Okay, so the cost varies directly, so k times the length of the call, k times m. A recent 5-minute phone call costs 60 cents. Write a direct variation model for this situation. So c equals km. We're going to plug in our k, our c and our m, 5 minutes, 60 seconds, or 60 cents. 0.60 equals k times 5. We divide by 5, divide by 5. This gives us k equals 12 cents. So varies directly tells us this costs 12 cents a minute. So our cost is 12 cents times every minute. There's our direct variation. Use your model to predict a cost of a 7-minute phone call. C equals 0.12 times 7. So the cost is 0.94, 7 times 84. Find the length of a phone call that costs $1.56. $1.56. So the cost is $1.56 equals K, or sorry, not K. We know what K is. K is 0.12 times M. Divide by 0.12, divide by 0.12. M equals, I'm going to use a calculator. 0.56 divided by 0.12, 13 minutes. So this is 13 minutes. So M equals 13 minutes. Okay, hopefully by this now you can see right down the cost per minute for phone calls is just 12 cents per minute. That's what a direct variation will do for you. The volume of a sphere varies directly with the cube of the radius of the sphere. You are given that a sphere with a radius of 14 centimeters has a volume of 11,500 centimeters cubed to 3 significant figures. Okay, so the volume of a sphere varies directly, so there's some constant, times the radius cubed, the cube of a radius. You are given that a sphere of radius 14, so the volume is 11,500 equals K times 14 cubed. So we got to use this to figure out what our K is. So 14 to the third is 2,744. 2,744 times K. We divide by 2,744 on both sides. 11,500. 11,500 divided by 2,744 gives us 4.19. K equals 4.19. 10 to the third, 274, 11,500. Okay, find a direct variation model. So this is going to be y equals 4.19 times r cubed. Use your model to find the volume of a sphere with a radius of 7 centimeters to 3 significant figures. So volume equals 4.19 times 7 cubed. 4.19 times 7 to the third. So our volume is 1,437.17. And it says to 3 significant figures, so we go 1, 2, 3, look to the right, 1,440. You come in. All right, so 1,440, somebody came to the door, and sorry about that. So this is approximately 1,440 centimeters cubed. Using 6 significant figures, find the percentage error between your model and the volume given by the formula V equals 4/3 pi r cubed for a sphere with radius 7 centimeters to 3 significant figures. All right, so the volume, the actual, is 4/3 pi times 7 cubed. Okay, so 4/3, so we go to our calculator, 4 divided by 3 times 7 to the third times pi. That gave us 1436.75. Okay, there's 6 significant figures. Okay, this one is 1440, so we subtract 1440, and we get negative 3.24495. So this is our error. This is how much we were off. We were over by this much. Okay, so we take this number and we divide it by the original. This is how you find your error. You divide it by your original. You can just go up to here and press enter, and that gives us our answer, 0.002. We were 0.002% off. Actually, sorry, that's 0.002, which is 0.2% off. All right, yay! The weight of an object varies inversely. Here's our first inversely one, with the square of the distance from the center of the earth. Okay, so our 2 unknowns are the weight. So the weight equals K divided by the square of the distance. So this is going to be distance squared. Distance squared. Okay? At sea level, 6,370 kilometers from the center of the Earth, an astronaut weighs 600 newtons. Okay? So now, if you don't know what newtons are, that's okay. You just keep doing the problems and go, I don't know what N means, but I'm going to just use that as my definition. Okay? So the weight is 600 equals K divided by the distance, 6,370 squared. Okay, so our number is going to be gargantuan. Okay, let's see. So we get. So if you guys look at this is times 6,370 squared times 6,370 squared. So 6,370 squared times 600 gives us this. So our K equals, and I'm going to write it in scientific notation, because 2, 4, 3, 4, 6, 1, 4, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 2.43 times 10 to the 10th. That's what our constant is going to be. So find a model. So this is going to be weight equals 2.43 times 10 to the 10 divided by our distance squared. The International Space Station orbits at an altitude of 408 kilometers. Okay, so this is 408 kilometers above the Earth. But we also know sea level is 6,370 kilometers. Sea level is just right on the Earth. The level spot where water goes to. So it's not a mountain and it's not a valley below sea. It's always at sea. So that's 6,370. The satellite is 408 kilometers up. So from the center of the Earth, this is 6,370 plus 408. 6,370 plus 408. 6778. So weight this is for question B, equals 2.43 times 10 to the 10th divided by 6778 squared. 2.43 times 10 to the 10th divided by 6778 squared. 528.936. So our weight is going to be 528.936. We're going to go three significant figures, 1, 2, 3. We look to the right. It's bigger than 5, so we're going to say 529 newtons. That's the weight. Okay, that's the weight of an astronaut. Okay, which is obviously it's going to be less than what the weight is at sea level. Find the required distance from the center of the Earth for the astronaut to weigh half of what she weighs at sea level. So at sea level, she weighs 600. So we want to find out how far this has to be. 300 equals 2.43 times 10 to the 10th divided by d squared. Okay, you can use your calculator to solve this. Okay, but I'm going to use algebra. So 300 equals 2.43 times 10 to the 10th divided by d squared. I'm going to multiply both sides by d squared, so I get 300d squared. And then I'm going to divide by 300, and I get d squared equals 2.43 times 10 to the 10th divided by 300. Square root. Punch this into the calculator. Second square root. No, not squared. Second square root. In brackets, 2.43 times 10 to the 10th. Close those brackets. Get out of there. And then divide that by 300. Press enter. 9,000. So the distance is 9,000 kilometers away from the center of the Earth to be half their weight. Okay? Great. Here's the on your own. So these ones are just basically very, very easy. No word problems or anything like that. Just getting you to understand this word varies directly, varies inversely. All right. Ciao.